Any other questions? Is the homework easy? Yeah, this stuff's not so bad. In view of the test, kind of just thinking ahead, what I have found on the exam is the part that people mess up on the most is the phasers. So homework 7, you may want to review. Just based on historical evidence, people do okay on Modi plots, tend to do okay on the filters, to mess up the phasers a little bit.
Could you just briefly go over finding the transfer function for the differentiator option?
So I don't remember exactly what the circuit looked like, but it was something along the lines, it was a 4-stage circuit. There was a non-inverting op amp. And then we had a cap here.
Yeah.
And then there was something else out here. I don't know. It doesn't matter. So, I mean, this is worth looking at just in general. And VR. And just to emphasize, VN is a source. I mean, I didn't draw a source circuit there, but there's a voltage source there. So it has come up in the past. It's something that looks like that. And I left off the ground. To look at this circuit, I think it's clear that this circuit's isolated. Does everybody kind of agree with that? The input impedance to the op amp is infinite, so to speak, or in other words, no current goes into the op amp. So when you analyze what I just drew as a box, or H1 of S, this is an isolated stage, and we can write this as 1 over R1 C1, S plus 1 over R1 C1. And if you want to call that VA or some such number or some such value, that's fine. Looking at the non-inverting op amp, again, by the same argument, if we have a voltage here, it doesn't matter what's under my hand, but if we have a voltage here, the output here behaves as the non-inverting op amp. So that's isolated as well. So you can write H2 of S is 1 plus R3 over R2. And that would be a VB there. That's independent of what follows and independent of what comes before. So again, isolated. Looking at this guy, here's our H3 of S. We can go back and redraw this in a kind of more generic style, where we have a circuit like this, where these are arbitrary Z's, Z1 and Z2. That's the inverting circuit for impedance. And here we can say H3 of S equals Z2 over Z1 minus sign. And so there's our circuit. And in this case, Z2 was R, or sorry, Z2 was R, R4 in this case, and 1 over SC2, which is SC2 R4. Does that answer your questions? Then we can keep going. Negative. Yeah. And then the same thing out here, H4 of S, 1 over R5, C3, S plus 1 over R5, C3. Are we in agreement? Any other questions on this? And we can tell this is a differentiator. We can go back and do the circuit analysis with CDV, CDT. And we did that a while ago. Or in the Laplace domain, S is equivalent to the derivative. So all those things come out. All right. So to look at this type of circuit one more time, let's do something again. Something similar, but maybe a little smaller, just to save ourselves some time. So here's again a three-stage circuit. And we can do everything that we've done. We can find the transfer function, multiply it out, do the way I've recommended that you find the voting plots. In this case, we should find that this winds up being h of s is 10 to the 3 over s plus 10 to the 3 times 10, and the same thing. So that was fairly quick, but does everyone agree with what I just wrote out? Should be able to kind of do these things by inspection. There's an H1 of S, an H2 of S, an H3 of S. And we should also recognize that these are low-pass filters, right? These are two low-pass filters. Effectively, we wind up having to form 10 to the 6 over S plus 10 to the 3 squared. And so we have a double pole at 10 to the 3 and no zeros. And we can go in very quickly, and I will do this quickly and maybe a little bit too quickly, but we can plot this transfer function and it winds up looking like 20 dB, 0 dB, minus 20, there's 3, there's 2, 1, 0, 4, 5, 6. And you should be somewhat familiar with this by now, so even if you're thinking I'm going too fast, that's okay, you can prove it to yourself later. We have minus 40 dB per decade slope once we cross the double pole, and for S less than 10 to the 3, we're constant. 20 log of 10 is 20, giving us the 20 dB. And we can put a little minus 6 dB correction in there, or 14 dB to be precise. The correction is minus 6 dB, giving us 14 dB. Does everyone agree with this? There is another way of looking at these things. So if you don't like this method, and there have been people in the past who don't realize it's what I introduced first, so maybe it's a little bit more intuitive. But if you look at this, this is H1 of S, H2 of S, H3 of S. And so, and you can also make note, this is a low pass filter, first order. This is a gain term, and then this is a low pass filter. And we can write first order if we wanted to. Well, if we think about this for a moment, our magnitude plots, our Bode plots of magnitude, is 20 log magnitude of h of x, or j omega. So again, whether we use j omega or s doesn't matter. In this case, this three-stage network, well, h of s is h1 of s times h2 of s times h3 of s. Right? It's just multiplied out. So we can actually substitute that in h1 of s times h2 of s times h3 of s. Well, when we consider magnitudes and we have multiplication, we can write this again as 20 log h1 of s plus 20 log h2 of s plus 20 log h3 of s. Right? That's the log property and taking advantage of the multiplication in the magnitude. So log of A times B is log of A plus B. That's an identity relationship. AB equals log of A plus log of B. And you saw that at some point, I don't know, maybe in high school or somewhere, maybe in college. But that's a relationship. So looking at this, well, what are we saying here? Well, arguably, this is a low-pass filter with a cutoff frequency of 10 to the 3. right? I mean, that's what that is. So we can go in and just our H1 of S is a low pass filter. And we can write that. That's at 0 dB. There's 0, minus 20, and we can throw a 20 in there, and then minus 20 dB per decade. That's H1 of S. Do we agree? Yeah.
Can you quickly review what it means to be that type of like filter?
Oh, just what does low pass filter mean?
What it means, yeah.
So, low pass filter is somewhat self-named. Pass the low frequencies. And attenuate the high frequencies. And again, low and high are qualitative terms. Low and high relative to what? Well, low and high relative to what? Is what I'm asking. Relative to the cutoff frequency. So whatever circuit we design here, whatever R and C we pick, that's what defines low and high. And so remember, the transfer function is the ratio of the output to the input. So at low frequencies, V out over V1 is 1. And if that's the case, then the output amplitude equals the input amplitude, and we're passing it. Does that answer your question? And on the same token, we can say high pass filter is the inverse of that. Pass the high frequencies and attenuate or stop. I mean, attenuate and stop are used synonymously here, because we call that the stop band. Low frequencies. And we'll put this aside because we'll look at 2 other filters today as well. So it's worth bringing up, and we're going to revisit that anyway. So here's our low pass filter, that's H1 of S. Do we also agree that for this given circuit, that's also H3 of S? So, comma, H3 of S, same part. Same LPF. And then we can also look at our K term. 20 log of K is right here at 20 dB. 20 log of 10 equals 20 dB. And that's H2 of S. So we broke these things down into parts. And we can, in multiple stage circuits, we can look at each stage individually. What's the advantage here? We can write down a low pass filter fairly quickly now, a first order low pass filter. If we know the cutoff frequency, draw a straight line in the pass band, minus 20 dB per decade at the stop. You can do that instantaneously. You don't even care how many stages are here. You can draw this magnitude response right away, or maybe a few minutes of thought, but hopefully fairly quickly. I mean, this is something we want to kind of be able to do quickly. Well, looking at this, and again putting the rest of our expression back up, which is under this guy. Very well. Oh, sorry. Low pass filter plus 20 log K, or the gain term, plus low pass filter. So that's what we've written out here, the same thing. This is K and dB, and low pass filter. Omega C equals 10 to the 3. Omega C equals 10 to the 3. Those are the 3 responses we've just drawn. What can we do now to get the total response? We can add them. In the dB scale now, these just add. It's that straightforward. We can go down here, 0, 20, minus 20, minus 40. We can start at 0, 0 plus 0 plus 20. 0 plus 0 plus 20. And I probably should have started further. We can look at 10. 0 plus 0 plus 20. 0 plus 0 plus 20. And interpolate in there. 0 plus 0 plus 20. And still 0 plus 0 plus 20. So I should have started further just to make it more interesting. And what do we have here? Well, minus 20 plus 20. So we're down here. Minus 20 plus 20. And there's our 40 dB roll-off that we can do the other way, and we can keep going. At this point, onward and onward, this point, minus 40 plus 20. And again, that's stage 1 contribution. That's stage 3 contribution. I did write them out of order. That's stage 2. That's stage 1. That's stage 3. That's stage 2. And so, when we have this multiple stage network, we can just construct the individual stages and add them in there. And some people are more comfortable doing this, and I don't disagree with it. You take the circuit that you know very well, and you draw the Bode response. You take the circuit you know very well, draw the Bode response, do the same thing, and then just add up the numbers. This is another approach, and it comes out of the fact, again, that the logarithm is distributed. So here's something we can do. Okay, any question on that? Kind of straightforward, I think. No surprises there. So to come back to this for a moment. Low pass filter, high pass filter. Can we build any other circuits with a single stage first order design? Can we do anything besides low pass filters and high pass filters? No. Single stage circuits. RC or RL single stage circuits. LPF or HPF only. And parentheses. Again, they are first order. Well, certainly, as we've seen, we can construct multi-stage circuits and build other filters. Why do we want to do that? So coming back to our, rather than draw it again, our first order low pass filter, what is wrong with this circuit? It's what? It's bad. Actually, it's useful sometimes, but I mean, why is it not as good as it could be? What does an ideal filter look like? We brought that up last class. So an ideal circuit looks like this. So there's our ideal circuit, infinite stop, or complete stop in the stop band. And so how do we get closer to this? So how can we get better roll-off or a better stop band? Roll-off is a term we'll start using. More poles. And we just saw that in this circuit. So this has a slope of minus 40 dB. It's steeper roll-off. And that's better. It's stopping the high frequencies more completely. There was a price. What was the price we just paid for it, though?
Another stage to the circuit.
Well, yeah, from a circuit design point of view, we use more footprint, but I mean more in terms of the Bode plot. And I have it on the previous version of this Bode plot, but I didn't put it here. There was a cost. There is a price. There's more correction. Is that what you're going to say as well? So here, we actually drop down to 14 dB. And so remember, every 3 dB is 1 over square root of 2, so at our cutoff frequency, or corner frequency, our output voltage is now half. 6 dB corresponds to half, and so we have half amplitude. So what was the price now of getting a steeper roll-off? Well, our passband has some attenuation, and it's going to kind of exaggerate this, but our passband has effectively become not as flat. And so in our straight line approximation here, yeah, we draw a straight line, but in reality, we know we have these corrections, we would fit some smoothing in there. And so the net result of that is our passband is not as flat, and that's the second desirable property. So we have two filter goals. Two goals with regard at least these particular filters. A flat passband, which means magnitude of h of j omega equals 1, or the amplitude of the output equals the input, and steep stop band. In parentheses, we can write infinite. So those are our two goals, and they are conflicting goals somewhat. We can do some tricks to make them not conflict as much, but ultimately they do conflict in some sense. So here we see it clearly. We get a steeper roll-off, a steeper attenuation, better attenuation in the stop band, and we lose some signal in our pass band. That's the price we paid. Can you do better than that with first order circuits? No. You can always increase the roll-off, and then you're going to have a penalty in the passband. We will see later today. There is kind of a way we can do it in second order circuits. And so that brings up now second order circuits. Is there another copy of the handout? They make it back. Thanks. I had an extra copy of it. I think I just drew on it. So, second order circuits. And I do want us to leave some space here, so if you have this written down somewhere, leave some room for some more stuff. And we'll look at our classic RLC series circuit. And again, we can look at the voltage across any of those components or a combination of those components if we're looking at V out over V in. And so, again, we can define VCS over V source S as our transfer function. We've done that a lot of times. We can do this somewhat by inspection. Actually, and before I launch into this, you know, the RLC parallel circuit is another iconic circuit. It's the one that will be on your homework. So the other circuit, but I should make a comment in that probably 40% of you miss the fact that the alpha is different on an RLC parallel circuit on the exam. And so alpha is circuit dependent. We've been over the series in the parallel. Don't just write R over L. So and alpha is coming back, so this is something that you're going to care about in a week and a half. All right, so looking at this circuit, we have gone over this. I'm going to do it quickly. S squared, R over L. Why R over L? because this is a series RLC circuit, and that's what alpha, well, 2 alpha is. I should say. There's our transfer function. How does this transfer function behave measuring across the capacitor? We can look at our limits, and we've done this. H of S, as S goes to 0, H of S becomes what? I'll keep the dominant terms. What's the dominant term in the numerator? There is only one term in the numerator. It's 1 over LC. We keep that. 1 over LC. And the dominant term in the denominator, well, that's going to 0. That's going to 0, but a little bit slower. And that's not changing at all. So we get 1 over LC equals 1. And then we can look at the other limit. It goes to infinity. And again, keeping the dominant terms over S squared, and that goes to 0. And we've done this a number of times, so we should all be in agreement here. What type of circuit is this if we measure the voltage across the capacitor? We're passing low frequencies, we're attenuating high frequencies. That's a low pass filter. What's our roll off? What's the slope of our stop band? I'm going to use this word a lot. The absolute value. So what's our roll-off? Well, we have a 1 over S squared, so that's 40 dB roll-off, or a slope of minus 40 dB. So measuring across the capacitor for an RLC series circuit, V out over V in, we build a second-order low-pass filter. RLC series, V out equals VC. Second order low pass filter. Now that said, it is a second order low pass filter. In the long run we can get 40 dB, but let's look at our first example there. So I gave us some values. We have 10 to the minus 3, 10 to the minus 9, and then this was 10.1 K. And we can plug things in there into our little expression, our transfer function. Let's put this guy aside and bring it back. So for those particular values, we wind up with H of S equals 10 to the 12 over S squared plus 1.01 times 10 to the 7 plus 10 to the 12. And hopefully I did that right. And if we factor this by coincidence, we get nice, clean factors. And check that, make sure I did it right. Oh, left off a 10 to the 7 in there. 10 to the 7. And an S. It's an awfully big 7, but. So, what does our Bode plot look like for this particular problem? Well, we have a pole, 0 is none, may as well write that down. Pole, 10 to the 5, 10 to the 7, S, less than 10 to the 5, again doing it back in the old way. The way I tend to think about it, 10 to the 7, less than S. Just less than. So what do we look at? The algebra. Substitute that in. ZL over ZR plus ZL plus CC, and then some rearranging to get this. What type of circuit is this? Well, we can do the same thing. H of S as S goes to 0. What's the dominant term in the numerator? Still S squared. What's the dominant term in the denominator? 1 over LC, because this is vanishing. This is also vanishing. And so what does this wind up going to? 0. And we can look at h of s as s goes to infinity. And again, the dominant term in the numerator, and now that's going to infinity squared. It's going to infinity as well, but much slower than that guy, so he wins or she wins. 1. And so what type of filter did we build now by just measuring across the inductor instead of the capacitor? It's a high pass filter. We attenuate low frequency signals and pass high frequency signals. So, capacitor voltage V out equals V out. Inductor voltage. We build a second order high pass filter. So we still have our high pass and low pass filters. We can get 40 dB roll off, though we haven't looked at that specifically yet. So arguably, we can improve on our first order circuits. Well, we have a third option. And we can plot the Bode plot if you're so inclined. We should be able to do it fairly quickly. This one piece of paper. 5, 6, 7. It's just the inverse of what we saw before. 20 dB per decade. There's 0, minus 20, minus 40, and then falling off, minus 60, minus 80. That's 40 dB per decade. 20 dB per decade. And the same crappy style of filter. 20 dB roll off in our area close to the pass band, which isn't really achieving much. But overdamped. Overdamped high pass filter. And again, that was fast. If anybody's troubled by it, go ahead and say something. Everybody feels good? Well, coming back to our circuit, we measured across the inductor, we measured across the capacitor. We have a nice third choice here. We can look at the resistor. Plus minus V out. And H of S in this case winds up being R over L, S squared, R over L, S, plus 1 over LC. And we can do the same argument we did just a moment ago. H of S as S goes to 0. Goes to, keeping the dominant terms, R over L over S, 1 over LC, and again, that goes to 0. We agree? There's an S in the numerator, S is going to 0, so our transfer function has to be going to 0. H of S, S goes to infinity. And what do we wind up with there? R over L, S squared, keeping the dominant term, and as I just shouted out, we also go to 0. So maybe this is just a stop all filter, which would be kind of cool. But we can look at some place in between. And that's what you did on the homework.
Okay.
We can rewrite this as 2 alpha S over S squared plus 2 alpha S plus omega naught squared. We haven't done that for a while, but that is familiar to us. So R over L was 2 alpha, omega naught squared. Is 1 over LC. What about looking, and this matters, at the resonant frequency? J omega naught. So as S goes to J omega naught, well, what happens in the denominator here? J omega naught squared is what? So this guy winds up being 2 alpha J omega naught over minus omega naught squared plus 2 alpha J omega naught plus omega naught squared. And in my world, those two add to 0. Everything cancels, and you get 1 at the resonant frequency. Which means this is what type of filter? It's a bandpass filter. You attenuate low frequency signals, you attenuate high frequency signals, and pass signals in the vicinity of the resonant frequency. Omega naught is the resonant frequency. So on either side of the resonant frequency, we pass signals. And so what are we left with there? V out equals VR, second order bandpass filter, BPL. Resistor voltage. And just for argument or illustration's sake, we can draw little curves, and this is going to look like this. Thinking about this for a moment, what are the slopes of the roll-offs for a second order bandpass filter have to be? (20 dB roll-off constraint). Each is 20 dB. You cannot do better than that with a single RLC series stage. Whereas these, in our particular examples, they were 20 dB in the short range, but we can make this 40 dB roll-off, we can make this 40 dB roll-off. You cannot do better than 20 dB on either side. And that makes sense from our analysis point of view. We pass a real pole, we have a slope change of minus 20 dB. We pass a real pole, we have a slope change of minus 20 dB. And so that's fixed. You can't do better than that with a bandpass filter with just one stage. Now certainly you can have a higher order stage, or more stages, as we'll see. We do have one more type of filter that exists. Does anybody know what it's called? There's a fourth filter.
Non-band pass?
Yeah, it's a different name, but yeah, I think you're on the right. Often called a notch. And so there's a notch filter. So we have our LPF, HPF, BPF. We have a notch filter. Or, as someone said, sometimes called a band stop filter. And so what does that look like? Now something like this. So it passes high frequency and low frequency signals and attenuates a band in between. Can we build this with an RLC series circuit? I gave away the answer earlier. No, it doesn't have anything to do with the damping. So I mentioned we measured across the capacitor, we measured across the inductor, we measured across the resistor. What else can we measure across? Well, we could measure across the source, but that'd be 1-to-1. That would be a pass-all filter. So we can measure across more than one component. And so if we look at our RLC series circuit, if there's our V out, If we think about this just from a circuit point of view, as frequency goes to 0, what do we do with the inductor and what do we do with the capacitor? Well, the inductor becomes and the capacitor becomes, and so the voltage across the capacitor as frequency goes to 0 becomes what? The source voltage, right? On the other hand, if we let frequency go to infinity, then the voltage across the inductor becomes an open circuit and the capacitor becomes a short circuit, and the voltage across the inductor becomes the source voltage. So on either limit, the output is equal to the source. We can again look at the resonant frequency. Well, what's another property of the resonant frequency that we brought up before? It's all the same thing, but we haven't said it explicitly. What is true about the resonant frequency in terms of impedances? Yes, but I was looking for a different way. At omega naught, ZL equals ZC conjugate, which means what? ZL plus ZC equals 0, which means the voltage across VL plus VC is what? Well, if the sum of the impedance is 0, what does the voltage have to be? 0. Backing up a step though, what does that mean? Does that mean the voltage across the inductor and the capacitor are 0? No. It means they're equal and opposite. So at resonance, this V out is 0. So this is omega naught. So at our resonant frequency. And we can find that out. S squared plus 1 over LC. S squared plus R over L. S plus 1 over LC. When is this 0? Well, again, this is equivalent to S squared plus omega naught squared over S squared plus 2 alpha S plus omega naught squared. When is the numerator 0? When j omega equals j omega naught, the transfer function becomes 0, and thus we build our notch filter. So we can measure across anything we want. In some sense, that is done. So we'll put it here, of course. So here's another option to build our fourth kind of classic filter, the notch filter. Everybody okay with that? And so here we have a 0 and still 2 poles. So we looked at overdamped case before we journey on to the other damping. Let's define something called the damping ratio. It's called the damping ratio. That's the Greek delta. Or the delta. It's something Greek. I should remember that. I always yell at the students about forgetting their Greek. It's not W, it's omega. The damping ratio is defined as alpha over omega naught. So there's nothing particularly new here, but it is some jargon that you should be familiar with. And so our overdamped case corresponds to the damping ratio being greater than 1. And so there's something we want to be familiar with, some terminology we should incorporate into our ECSE knowledge base. So this is the definition of the damping ratio. Good thing for the crib sheet, I suppose, so hopefully you'll memorize it, but it's just the ratio of the attenuation constant to the resonant frequency. And overdamped greater than 1, and we can even add strongly overdamped much greater than 1. the orders of magnitude greater than 1. What does that mean for us? Well, if the damping ratio is greater than 1, coming back to a question we asked a little bit ago, do we want to build a low-pass filter or a high-pass filter? No. I mean, these are not good filters. The roll-off is bad. You haven't gained anything. So, not a desirable case for a low-pass filter or high-pass filter. On the other hand, arguably, maybe you want to use it to build a bandpass filter, a wide band filter. So, some of the terminology maybe you've read about in communications, wide band, large frequency bands, not near as large as what we're looking at, where we're talking about 2 orders of magnitude. The FCC would have a fit, but they make okay problems. But wide band filters, 2 poles, far-ish apart. So, and similarly, we could have critically damped, which again is a special case. The damping ratio equals 1. Alpha equals omega naught. Is this potentially a desirable low-pass filter or high-pass filter design? Yeah, maybe. And then underdamped, of course. Less than 1. And then we can go ahead and again say strongly underdamped if we're so inclined. A lot less than 1. And of all of these, which one probably makes the best second order filter designs? Underdamped. We'll do that last. So, we can go back to our RLC circuit. That's a 3. And we can again plug in H of S equals VC of S over the source of S. Plug in some numbers. We wind up with 10 to the 12 over S squared plus 3 times 10 to the 6 S plus 10 to the 12. And hopefully we all agree that's 10 to the 6 S plus 10 to the 6 quantity squared. So now we have a double pole at 10 to the 6. 0 is none. None. Poles 10 to the 6, double. This actually looks familiar. If we go ahead and plot this, we recognize, or we can write this one more way, 10 to the 6 over S plus 10 to the 6, 10 to the 6 over S plus 10 to the 6. Effectively, what is this? What's that? It's a low-pass filter of what order? First order. So we have this RLC series circuit that is equivalent to 2 cascaded first order filters. So we can build this particular transfer function with both a second order circuit or cascaded first order circuits. And that's true of critically damped and underdamped. So either critically damped and overdamped. Let me say that correctly. Critically damped or overdamped, you can build with either first order circuits cascaded or a second order circuit. Well, in that case, have we really gained anything? Not particularly. But 0 dB. M6, 5, 4, etc., etc. Then we can add our correction here, minus 6 dB. What's nice, we have 40 dB roll-off. What's bad, we have minus 6 dB at our cutoff frequency. And this now does become a little bit more meaningful. This is omega, this is our double pole, of course, at omega C equals 10 to the 6th. And that's not an unreasonable thing to do, barring some kind of, again, general convention of what the passband is defined as. So again, a little bit more terminology for you. Passband is usually defined, not always, as the frequency range that varies within a 3 dB fluctuation. That varies within 3 dB. So what does that mean for this second order critically damped circuit? Well, in a kind of general sense of the passband, we've actually reduced the passband. We would have to go find out where that 3 dB point is, somewhere off to the left of 10 to the 6th, and that would be a more explicit version of our passband. I don't follow this as a strict definition. In this particular case, for our critically damped circuit, I can reasonably call this the cutoff frequency of 10 to the 6th and call that our passband S less than 10 to the 6th. But in a more common definition, well, I have too much attenuation here to consider that part of the passband. You know, this is not a vital thing to internalize, though, again, in the general sense, this is often the definition of the passband, something worth knowing. But in this case, recognizing that we have a double pole at 10 to the 6th, or minus 6 dB there, fair bit of attenuation, that matters. So we pay the price, but there's our critically damped case. All right, so I'll give you a couple minutes, stretch your legs. Realize we're all antsy because spring is here. People would rather be outside. Rather be sleeping? Is that what you said?
No, I am.
You are sleeping. I can be louder.
Sing a lullaby.
What's that?
Never mind.
Again, we talked about voltage across the capacitor, voltage across the inductor, voltage across the cap being the low pass filter, voltage across the inductor being the high pass filter. They're both kind of symmetric versions of each other. So the cutoff frequency is a minus 6 dB point. We have 40 dB roll off. They both can be achieved using low pass filters as well, first order circuits as well, I mean. So not a tremendous amount of gain, though we can do it with second order circuits. The band pass filter looks a little bit different. It is a little bit harder to think about. And we'll come back to that in just a second. I want to look at underdamped first. So, same circuit. K, use 1K first, 10 to the minus 3, 10 to the minus 6, and And so h of s in this case equals 10 to the 12 s squared plus 10 to the 6s plus 10 to the 12. And so now we're underdamped. And this is a specific underdamping that actually has some meaning. Alpha is 5 times 10 to the 5, omega naught is 10 to the 6, and so our damping ratio is 1/2. And that's actually a fairly significant number that has some meaning for us. And so let's look at our Bode plot. We no longer have real poles, right? So what can we do? Well, in the limit, we can again say h of s, as s goes to 0, goes to 1. I didn't fill in all the steps, but that hasn't changed, and I should define it. This was VC of s, or the source of s. So that is our capacitor voltage, plus minus V out. So there's our limit. In the other limit, again, nothing's changed here. H of s as s goes to infinity, goes to 0. Or more specifically, we can write it as 10 to the 12 over s squared, which is 40 dB per decade roll-off. Right? 1 over s squared is 40 dB per decade roll-off. So in the limits, our straight line approximation is accurate. And so I can go and I can put up our Bode plot 4, 3, 2, 7. In the limit, I can start with the critically damped Bode plot. 0 dB, minus 20, minus 40, minus 60, etc. Should have changed the scale a little bit just to make it easier to draw. There's my critically damped plot. Right? There's our straight line approximation. And in the limits, as we get far away, this is accurate. So I can draw a big bold line and a big bold line. And no matter what the underdamping is, that's a reasonable thing to do. Now, one thing I've done here is here's my critically damped case. The critically damped cutoff frequency was 10 to the 6, but for this circuit, there is no real pole, but 10 to the 6 is what? What is 10 to the 6? It still has meaning for us. Specific meaning. I wrote it up there. It's under the piece of paper. What's 10 to the 6? It's omega naught. It's our radial or resonant frequency. Which for the critically damped case, omega naught and cutoff frequency were the same. Yeah, it's worth writing down somewhere. You know. Critically damped. Omega naught equals omega cutoff. Or corner, or whatever terminology you want. A little side note there. Well, as I look at the underdamped case, I still work with that omega naught. I still work with that resonant frequency. And so, at that point, at omega naught, we can actually evaluate our function quickly. At omega naught, evaluate magnitude of h of j omega naught. Not 20 log specifically, but that's something we can do quickly. I mean, half of it we don't even have to think, which is always good news. So h of j omega naught always winds up being, in this case we have omega naught squared minus omega naught squared, that was 1 over LC there, plus 2 alpha, j omega naught plus omega naught squared. Just substituting in at omega naught, right? We've already done this once, no problem. These guys cancel. Winds up being omega naught squared over 2 alpha, omega naught, there's a j in there. Well, that cancels, that cancels. But we've also defined our damping ratio as alpha over omega naught, right? We did that math already. Or omega naught over alpha equals 2, and that winds up being 1 over j, 2 over 2, and magnitude of h of j omega naught equals 1. Because the magnitude of j is 1. Is everybody comfortable with what I just did? I didn't explicitly fill in a couple steps, but everybody agree? Well, then what's our dB? 20 log at h of j omega naught equals what? So what have I just done? At this point, I have 0 dB, and that's a point I can know exactly. H of j omega naught, no. Without much work. I mean, we can always know any point by plugging it into our calculator or MATLAB, like I'm inclined to do, or whatever the case may be. But this one we can do by observation. We can do on paper. And so that's good news. So that's a 0 dB point. What did we just do then? We underdamped our circuit, and what effect did we have? Well, what did we do to our passband? I mean, here in our critically damped case, you know, we can draw a little bit, and we're down at minus 6 dB at 10 to the 6. We underdamped the circuit. What did we do with the passband, effectively? Yeah, we kind of leveled it out. So here, you know, we've arguably improved the filter response. We have a 40 dB roll-off, and we have a flatter passband. Now, in reality, this actually has a little bit dip above 0 dB. And so there is a little bit of a bump in there. And then it comes down and follows our 40 dB, which I didn't draw very well. So here's our new filter response. At our corner frequency, it's a 0 dB point. Our passband is fairly flat. And that was with a damping ratio of 0.5 or 1. H of j omega naught equals 1, which implies a 0 dB point relative to the passband. Flattish passband. 40 dB roll-off. Better. Cascaded first order. To get 40 dB roll off with first order circuits, you cannot do better than minus 6 dB at your corner, or whatever you define your corner to be. You can certainly shift your corner to accommodate that, but it's arguably not gaining anything. You could argue that it would, but with an underdamped circuit, with an underdamped RLC, second order response, you can flatten the passband and get that 40 dB roll off and improve things. And so this is a fairly significant one. Another one we can look at is same circuit. We can say 1.41K, which should be a number that's a little bit familiar. What does 1.41 remind you of? Square root of 2. So that's square root of 2 times 1,000 K. And so if we look at that, then now we have a damping ratio of 1 over square root of 2. Which is a little bit larger or a little bit less underdamped than 1 over 2. And we can go through all the same process again. If we look at H of S over VC of S, over V source of S, and again 10 to the 12 over S squared plus 10.41 times 10 to the 6S plus 10 to the 12. We can do the same arguments. Again, nothing's changed. H of S is S goes to 0, goes to 1. H of S is S goes to infinity, goes to 0. So it's still definitely a low pass filter. And then we can look at H of J omega naught. And again, the expression is the same. And that winds up being, if we look at the magnitude, 1 over square root of 2. That's another kind of meaningful-ish underdamping. So 1 over square root of 2. What does that mean? At omega naught, what would our correction be in terms of our critically damped case, our correction to our critically damped straight line approximation? Well, what's 20 log 1 over square root of 2? You know this. Negative 3. So have we achieved anything? Well, the same type of reasoning. You know, this was damping ratio of 1/2. We can do a very similar type of plot. Here's our straight line approximation. Again, in the limits, it's going to be accurate. Our correction now, minus 3 dB. And again, is that better than cascaded first order circuits? Sure. Here our correction is 0. 0 dB correction. You can write it out for completeness. Minus 3 dB correction. And again, we're talking about correction to the straight line approximation of the critically damped response. So the critically damped case is our relative case. And here's our correction. And this is 1 over square root of 2. Why do that? Is it better than 1 over 2? It kind of depends what your goals are. This goes back to what I talked about, the pass band being the 3 dB variation. And so, well, 1 over square root of 2 does bring us in to our 3 dB variation, 0 to minus 3 for our low pass filter cutoff frequency at 10 to the 6. That's fine. You know, we have some curve down in our pass band instead of some bump up. That's okay, depending on what your needs are. So it depends on your specs, but these are kind of, again, classic values. And occasionally in between, but for second order circuits, these are good metrics, good operating ranges. Well, let's really kick things up. Let's underdamp the hell out of it. See what happens. And again, we're still measuring across the cap. So let's make that 100. 10 to the minus 3. 10 to the minus 9. Transfer function hasn't changed. H of S is still 1 over LC, S squared plus R over L, S plus 1 over LC. Nothing's changed there. I haven't written that out for a while, so probably a good time to do that. S squared plus 10 to the 5th S plus 10 to the 12th. And again, we still start with the critically damped case. As soon as we're under damped, start with the critically damped approximation. Our resonant frequency, which would be our cutoff frequency of the critically damped case, is at 6. And so we can start here. So there's our critically damped 0 dB, 6, 5, 7, 40 dB roll off. Critically damped approximation. And again, in the limit, everything has to be consistent. We've already done this a bunch of times. We know as S becomes small, it's 0 dB, and as S becomes large, it converges to the 40 dB roll-off. So that's accurate. What happens in the vicinity of the resonant point is the big question. And we could draw this a little further and be conservative here. So let's look at H of J omega. In this case, J 10 to the 6, omega naught 10 to the 6. And once again, I hope we agree these two terms are going to cancel. We are looking at magnitude, so I'll just draw that in right now. 10 to the 12 over 10 to the 5 times 10 to the 6 equals 10. So we're strongly underdamped, and now the magnitude of the transfer function at the resonant frequency is 10. Well, on dB scale, what's that? 20 log of H of J omega naught equals 20 dB. Well, what does that mean for us? We're up here. 20 minus 20 minus 40. And so what does our plot do? Something like this. It actually goes up a little bit. Is this now a good low-pass filter? Yeah, probably not. Unless you're trying to do something kind of strange. So, but this is a real response. So if you have an underdamped circuit and you're building a filter and you do it poorly, this is what happens in the vicinity of the resonant frequency of the circuit. And you've all probably heard that at some point in your life. That's a real thing. And we'll do that in the lab and you'll see it. So the trick here, when we look at underdamped circuits, critically damped and overdamped circuits, you do Bode plots the same way you did in the homework that we just finished. So homework 8, find the real poles, find the regions, find the slope, and then in terms of phase, which we haven't looked at today, do the same thing. Cross a real pole, no worries. For an underdamped second order circuit, you cross the resonant frequency. The resonant frequency is the thing of interest. Maybe that's worth writing down. So for critically damped, overdamped, critically damped, Bode plots, as homework. Find real poles, zeros. Regions, etc. Underdamped. Use critically damped approximation. Find correction at omega naught. We put quotes around correction. And so that's the fundamental difference here. As we use the critically damped approximation, we find the correction at omega naught. So we're still going to have the same, in this case, 40 dB roll off. We still have omega naught as our effective pole. And then we find the correction. For a damping ratio of 1/2 or larger, and less than 1 for completeness, since this is underdamped, correction is still negative. And that's what we saw. That was our damping ratio of 1/2, which being 0, which mean just greater than 1/2 would be slightly negative. And then 1/2 correction is positive. In other words, at the resonant frequency and someplace before it as well, our dB value is higher than the past band. And arguably we could call this strongly underdamped, though. Again, that's a little bit of a fuzzy description. So these are the things that we look at. Everybody okay? Now the bandpass filter has its own little tricks, its own little quirks. To come back to our strongly underdamped case here, we established this was a 20 dB correction. That was the one we just looked at. So R was 100, L was 10 to the minus 3, C was 10 to the minus 6. Well, in this case, we found L, or omega naught, was 10 to the 6, and we can find alpha was 5 times 10 to the 4. Well, what's the height of this? This is 20 dB. In this case, we have a damping ratio of 1/20. The height of this distance here, always is going to be 20 log of 2 times the damping ratio. That's the correction that we were just talking about. And that's something worth noting. I mean, we're going to use that over the next 20 minutes or so. So certainly we can go and plug stuff into the transfer function, which is essentially what I did here. But equivalently, we can use this relationship. It's a shortcut to what I just wrote down. So the height of that, 20 log of 2 times the damping ratio. And that checks. So we're not going to stop class early, so you don't have to worry about it. So let's go back and look at our band pass filter. Critically damped band pass filter. This is a little bit more tricky per se. So we're looking at H of S, goes R over L, in this case RLC series circuit, R over LS plus 1 over LC. And again, we can write this as 2 alpha S, S squared plus 2 alpha S plus omega naught squared. So just writing things out symbolically. Well, if we're critically damped, alpha equals omega naught. And for completeness, our damping ratio is 1. Arguably, in our low pass filter and our high pass filter, for the straight line approximation, what is our correction at the double pole? Yeah, someone said it. You can say it louder. -6. So for a double pole, which is the critically damped case, we have a correction, -6 dB correction. At double pole to the straight line approximation. That's what I just said out loud. Squeeze that in there. And that was clear. I mean, we've done that a couple of times already. There's our -6 dB, there's our straight line approximation, -6 dB at the pole, that's one of our rules. Well, for the band pass filter, what do we look like? What does it look like? Well, we already know it's 20 dB roll off on each side. It's critically damped. There's 10 to the 6, 5, 7. There's 0 dB. Well, I need to be a little bit careful here. So, my inspection at omega naught for the band pass filter, what is the magnitude of H of j omega, or H of j omega naught? We've already done this a couple times, but what is it always going to be? If you plug in j omega naught to that expression, 1. Always. For the band pass filter, doesn't matter what the damping is. H of j omega naught, magnitude equals 1. What does that mean for us? At omega naught, we have a 0 dB point. Always. So we plug in H of j omega naught, it's a 0 dB point. Doesn't matter what the damping is. Overdamped, underdamped, critically damped, at the resonant frequency, the band pass filter is a 0 dB point. Kind of a special point, I suppose. But a little bit meaningful here. Well, that's kind of two rules together. At H of j omega naught, the magnitude of the transfer function is 1, which is a 0 dB point. It's also a -6 dB correction relative to the straight line approximation. Well, the straight line approximation is 20 dB roll off to each side. So what does that mean with regard to our straight lines? That should go like this. There's our straight line. 20 dB roll off. And they kind of form an inverted V with a vertex that's 6 dB above. There's our correction, so if we were to add the true plot, you know, a little dashed line in there. H of J omega naught, it is a 0 dB point at that point. The output and the input have the same voltage magnitude. But our straight line approximation vertex is 6 dB above that point. And that's fairly meaningful, fairly useful, I should say. Not useful in the sense, but in understanding how things are plotted. That's fairly useful. Let's go back a little bit backwards and consider our underdamped bandpass filter. So we could say we were at 10 to the 5th, 10 to the 7th were our real poles, we had 20 dB roll-off. I meant to say overdamped. Sorry. There's our 20 dB roll-off on either side, so this is the critically damped case. And here's our overdamp. And we still have 20 dB roll-off. So the slope of both of these. That's a minus 3 dB point, that's a minus 3 dB point. To fully draw everything. So that's a minus 3 dB point. We still have a resonant frequency of 10 to the 6th, that's omega naught. That's omega naught. And so that's 0 dB right there. Again, that was independent of our damping. So that's 0 dB. Well, I could do something a little bit silly. And why not? They could draw those straight line approximation extended. So that looks a little bit like what we have up here. I could take these roll-off lines, extend them, and find the vertex. This distance, like we just said a second ago, 20 log 2 delta. 20 log 2 times the damping ratio. What's the damping ratio for the critically damped case? It's 1. What's 20 log of 2? 6 dB. 20 log square root of 2 is 3 dB. That's the inverse. 1 over square root of 2 is minus 3 dB. That means square root of 2 is 3 dB. So here's a nice way of plotting bandpass filters and knowing where to put our straight line approximation. Now we've gone back and said, or I've said, overdamped case, you know, you don't need to do this. We can just use the tools we already have. But this gives us insight into it when we look at the underdamped case, which is a little bit more complicated. So for our underdamped case, again, the same circuit, nothing's changed. 10 to the minus 3, 10 to the minus 9, and we can do 100 here. So what does that mean for us? Well, we still have a resonant frequency at the source, of course, and now we're measuring it across the resistor for the bandpass filter. There's omega naught. And at omega naught, we always have a 0 dB point. Where do we draw the straight line approximation to get our limits? We know it's 20 dB roll off on either side, but where do we put it? Well, we go back. So omega naught's 10 to the 6. Alpha 5 times 10 to the 4. Damping ratio of 1 over 20. And so what's 20 log? 2 times the damping ratio. Well, that's minus 20 dB. That's the vertex of our straight line approximation. So here I can do something, draw some dashed lines. That's minus 20. That's minus 40, minus 60, etc. Well, there's our straight line approximation that the body plot has to converge to as we get far away. So I can go ahead and fill that in. That distance minus 20 dB. And here I can just be a little bit fuzzy. You get something that looks like this. And that's a real thing. Is that useful? Actually, it is. It's a narrow band pass filter. It can be pretty useful if you're trying to get a very narrow channel. Rapid attenuation, this is probably the most useful out of all the second order filters we look at. So this one a little bit practical. So the trick here, when we sketch these things, this one's a little bit different than the other rules. The critically damped case always has a straight line approximation. That's this upside down V. But the upside down V moves up and down depending on the damping. Critically damped case, the upside down V vertex is 6 dB above the 0 dB line. That's always true. As you over damp it, that vertex moves up further and further. As you under damp it, that vertex moves down. And you get the band pass filter narrower, which is a useful achievement probably in many cases. You do really want a narrow band pass filter. All right, any questions on this? Okay. You have me a minute now.